Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, we discussed during the last few sessions, that is the neutral environment and the different effects of the neutral environment, that is the atomic oxygen attack, and then we have seen what are the effects of atomic oxygen attack and what are the how you can mitigate those effects. Then the atmospheric drag because of the neutral environment, the deorbiting of the spacecraft. Then we have seen that is the hypervelocity impacts of the micrometeoroids as well as the orbital debris. And then we discussed the debris monitoring, capturing and removal techniques. So, now today we will start the environment which is called the plasma environment. So, what is actually plasma and its the nature, that we will try to understand, and how the plasma behaves in the external electromagnetic field. We will consider the cases for the uniform magnetic field, and then we will derive the expression for the gyro radius and the cyclotron frequency. So, what is plasma? So, plasma is basically the fourth state of matter, that is the gaseous state, but it is ionized, there is no neutral particles, but collectively this plasma is the neutral, and through this discussions we will try to explore the various the striking the characteristics of the plasma and how the plasma environment affects the the spacecraft system. So, in order to do that, we will start with the basics, that is how what is the behavior of charged particles in the magnetic field. So, we will start with a single particle, though I said the plasma is the collective behavior, it is not defined by a single particle, but what we will do just to have the basics, to start with the basics, we will do that. Once we do that, then we will consider the collective behavior of the particles by considering their different energy distribution. So, all these things we will do. Today we will start with that is the moving, that is the a moving charge particle in an EM field. So, this is we will see what happens to the charge particles. So, let us consider a charged particle of mass m and charge q is moving at a velocity v in an arbitrary direction in an EM field. So, here we will consider the uniform as well as static EM field. So, what is uniform? By uniform I understand that is the flux, the flux density or the number of flux lines, it is not changing when the electromagnetic wave is propagating. So, the cross section is that is the number of the flux lines in a particular the cross section is constant. So, that is why I am saying it is a uniform, and static means I am not considering here the temporal or the time change behavior. So, once it will be clear, that is why I am taking the static case. So, when a charge is moving in an electromagnetic field, then it experiences a force that is called the Lorentz force. So, it is Lorentz force So, Lorentz force is given by F E and the cross product of the velocity vector and the magnetic flux density. So, now we will consider the case 1 we will consider, we will consider the different cases. So, case 1 we will consider that E is 0. So, only the magnetic field which flux density is given by B. So, this is possible only when I consider the static case. In dynamic case there cannot be if there is the magnetic field, change of magnetic field will give you the electric field, change in time change of electric field will give you the magnetic field. So, but in static case we can consider this. So, now I can write this, the force is equal to Q, that is the cross product of this. Now, the force F is I can write is the mass into acceleration okay. So, I can this, so this expression I can write, this is equal to d B by dt is equal to Q by M then B cross product of V. Okay. So, now we will assume, let us assume the B is z directed. So, I will write it like this, and the velocity vector, that is, as I already considered, it is an arbitrary, it is moving in arbitrary direction. So, we will resolve its 3 components, there is x component, y component and the z component. So, now we substitute this to in our this expression what I wrote in the previous slide. So, it will be d of V x by dt x, then d of V y dt, that is y directed, then d of V z by dt z directed, and then that will be equal to q, then V, this 3 components V x x, then V y y unit vector, V z z unit vector, and then the cross product of 0 x, then 0 that is y, and then B z. So, this you can write in the determinant form. So, it will be x unit vector, then y unit vector, z unit vector, then you will have this V x, V y, V z, then 0 0 B. So, now I can write this 3. So, it will be q, then B y, B, then it is x, y component will be minus V x q. So, here it will be q by m, we need to write q by m. Yeah. So, q by m, V x B, then y, and the z component is 0, the z component is 0. So, now I can both I can equate the each component of the both side, and I can write that is d B x by dt, that is equal to q by m V y V. So, I will write this as equation, some equation I will write. So, I will write this as equation 1, then I will have the equation 2 as here I will write the equation 2 d B y by dt is equal to minus q by m V x B, and then dVz by dt is equal to 0. So, now what we will do? We will differentiate the first equation with respect to t, and then we will see how what equation I get. So, what I will do? We will differentiate it the first equation. So, I will get dt square, it will be q, then b y, then d dv. So, it will be dv y by t. So, it is b. So, it is only b. We have taken only the z component of b. So, this is only b, and then it is divided by m. So, now I can substitute the dby by dt from the equation number 2. So, I will be able to write d square bx by d square, this is equal to minus q square by m square into b square into Vx. So, this I can write then equation d square Vx by dt square, this is plus q square by m square b square Vx is equal to 0. And similarly, if I differentiate the other equation, that is the second equation, and substitute the first equation, then I can write d square b y by dt square plus q square by m square b square b y is equal to 0. And if I integrate the third equation, then I can show that b z is equal to, so b z is equal to constant. So, what is b z here? So, b z is parallel to the magnetic. So, b z is the parallel component to the magnetic field, and b x square plus b y square, this is the perpendicular component to the magnetic field. Okay. So, now what we will do, that let us see what are these two equations. Now, these two equations, I will write it equation number 3 and this is equation number 4. So, equation number 3 and 4 are equations 3 and 4, they represent that is the differential equations, for a simple harmonic motion. And what is the the standard form of this simple harmonic motion? If I put that one, then I should write these two expression as d square v x by dt square plus omega c square v x is equal to 0 and also d square v y by dt square plus omega c square b y is equal to 0. Okay. So, these are the before I do further things, I will just like to tell you here the effect of the magnetic field. You see the velocity, whatever the original velocity, that is z component of velocity, it is not magnetic field has not done anything on this parallel component. So, it is as it is, the particle is moving in the linearly along the direction of the magnetic field. But these two equations, and now let us see from these two equations whether we can derive this what is the trajectory of the particle. So, these two equations they are since it is the simple harmonic motion. So, here what is called the omega c is the angular velocity, So, this is the velocity of oscillation or the velocity with which it is moving or it is having the oscillations. So, what is this omega c? If you see this omega c square is equal to, we have put it like that. So, it is q b by q square b square by m square. So, I can write omega c is equal to plus minus q b by m. We will see what is So, plus and minus, if it is the clockwise or counterclockwise, then it will be plus minus. Another thing is here, q can be positive, q also can be positive or negative, depending on whether it is an electron or it is an positive ion. So, we will see that is how we do this. When a electron is moving in a magnetic field, what will be its the sense of the rotation, or that we will see after we derive the other parameters. So, this is called the cyclotron frequency. This is called the cyclotron frequency. So, its unit will be the radian per second. You can convert it to hertz by dividing it by twice pi. Okay. This is also in fact, this is actually the general term is the frequency of gyration. Okay. Now, what is happening because of the because there is magnetic field is not operating, or magnetic field is not changing the axial velocity or the velocity component along its direction, that is the parallel to the magnetic field, but it is exerting a force, the magnetic field is exerting a force. What is that? That is m, not m, it is q. So, q b perpendicular. So, there is two components, as I said, the velocity along the magnetic field direction, and the other component is the perpendicular to the magnetic field direction. So, whatever it is the perpendicular to the magnetic field direction, so that is acting. So, this is the force working on the particle, and that force is, this force is perpendicular to. So, this force is perpendicular to the velocity direction. So, because of that, what will happen? Because of, so this, since the force is perpendicular to the velocity direction, so what it will do? So, this is acting something like a centripetal force. So, this is something as centripetal force. So, this F is like a centripetal force. Now, what is centripetal force? So, centripetal force is m v. So, here it will be perpendicular v by r c. So, we will consider this radius we will put as r c, or I can put it here also. Yeah. So, this is r c. So, this as if there is when there is a circular motion, this, so there will be centripetal as well as there is a centrifugal force. So, what will be the centrifugal force here? That is the force what is no. So, this is the centrifugal force. Centripetal force is here that is the q cross b, and these two are perpendicular. So, I can write this as q b. Okay. So, this centripetal force, this is the centrifugal force. Now, these two quantities should be, I should be able to equate this quantity, and I should put a minus sign here, because the two forces are in the opposite direction. So, I need to put a negative sign here. So, I will write it here. So, I will write Q B. So, now we can get I can get this R C value. So, this how I can, so this R C value will come. So, this R C will be equal to minus, so it is Q into B divided by M. Okay. Now, we have seen this quantity Q by M. So, this I can write as, this is our the cyclotron or the angular frequency. So, I can write this as, so omega 3 by d. Okay. So, this is the formula for, no, I think this should be, because it is 1 by R C, this is 1 by R C. So, my R C is equal to this is the omega c. So, in this case why I have taken this is as a minus, because I am putting this Q B by M as minus omega c, because here we will consider here the charge, that is the sense of this W c sense. When the charge is negative, we will consider it as a counterclockwise. So, we will consider this as a counterclockwise. So, you see here when it is minus q, I am putting the direction is changed. So, from this point I can write this as the R C, because R C cannot be the negative. So, this is called the radius of gyration. So, this R C, what we have written, this is my V perpendicular to omega c. So, this is the radius of gyration, or Larmor radius. Okay. Now, this two equations we wrote the differential equations, that was the d square b x by dt square plus is equal to m c square b x is equal to 0, and then d square b y by dt square So, since there this simple harmonic motion, I can write V x is equal to V t, V perpendicular, then cos of omega c t plus psi, and then B y So, what is this B perpendicular here? So, B perpendicular here is B x square plus B y square, and what is this psi here? This psi is the phase angle, it is the arbitrary phase angle at t is equal to 0. So, this also you can find psi will be equal to tan inverse of V y by V x. So, this represents, so whatever already we have shown you by the the concept of force, but if I solve this equation, this represents the equation of a circle. So, this basically the equation of a circle, and now what will be the trajectory? Now, if you see, it is having in the xy plane, it is having it is a circle, that is circle, but in the z direction it is moving. So, it means that the particle will have a, that is the particle movement will be. So, what I was saying, that is in the, if I draw this xy thing, so this is x axis, this is y axis, and this is the z axis. So, this is the direction of the magnetic field is the z directed. So, the particle will have its movement like this. So, this is the radius of gyration RC, and it is gyrating with the frequency, that frequency is the omega c or the cyclotron frequency, and here it is moving at the velocity of the v z. Okay. And at this plane, what is called in the xy plane, it is the circular. So, it basically the path is a helical path. So, it forms a, it is called the helical path. This is the trajectory of the magnetic field. So, we have seen, suppose if a charge is moving or a plasma particle is moving in an arbitrary direction in a uniform magnetic field, then the magnetic, in the direction of the magnetic field, the charged particle moves in a helical path, that is called, it is called also the gyration. So, this is a very important property, that is how magnetic field traps a charge. So, this is the mathematically we have shown it. So, in the next class we will still see the other aspects of a charge moving in a magnetic field. Okay, thank you very much.